Hey guys, welcome to our second section here, acceleration. We're going to do our video notes for this section here. So we're talking about the concept of acceleration. And so basically the accelerating objects are things that are changing their velocity. And that's the piece that is the most important here, right? Changing the velocity is what's going on. And the three controls on a car, the three controls that cause a car to accelerate are obviously the accelerator or the gas pedal, right? We know that one. It's the brake pedal, the thing that slows us down, of course. And the third thing that we may kind of not realize is it's the steering wheel, right? If we remember, velocity has both a magnitude and a direction. And what our steering wheel is doing is it's changing the direction even though I could be going the same speed. So for example, I could be going 60 miles an hour down the loop, and when I take those big turns, the direction changes. So even though my velocity remains constant, the direction changes. So that's why the wheel here is a good example of something accelerating. So an object is accelerating. A couple of things is true here. It can be changing its speed, right? It can be moving in a circle. We talked about that a little bit. However, if we take a look at these other ones, extremely fast, well, just because something is moving extremely fast, that doesn't necessarily mean it's accelerating. Downward, well, we need a little bit of information than just downward. And if something is accelerating, that means its velocity is changing, so that part definitely doesn't work there. So if object is not accelerating, that means the thing is probably moving with a constant speed, so we know for sure that B would be a thing. And it's slowing down, well, that's accelerating, so that doesn't work. Not accelerating, well, maintaining a constant velocity, that would also be true. And at rest, yeah, if an object is just sitting there, then I'm pretty sure, then yeah, it's not accelerating. So the next thing we have to talk about here is acceleration as a rate quantity. So here's my formula for it here, written out. Looks a little bit different sometimes than it does as we look at a thing here on the text. But acceleration would equal to delta V over T. And using the variables we were using the other day, that would be VF minus V naught, or original, over time. So I have an object with an acceleration of 10 meters per second. Circle all that apply. Well, I know for sure that it would change by 10 meters per second every 1 second, right? So if we think about the units here, what's going on? This 10 meters per second squared, what that's actually telling me is 10 meters per second every second, right? So there's a velocity change per unit time here. The other thing that applies here, it would have a velocity of 100 meters after 10 seconds. That's assuming it's starting from rest, right? So both of these, look at these, have a change in velocity that they're looking at. Here we're looking at a change in position, so these two guys don't apply there if we're looking at just the change in position. So I have a couple of different scenarios here. I have a few different ways that we've expressed acceleration here. So I'm going to look at this. I'm going to sketch it out here. So I have 0 miles per hour at t equals 0 seconds. 10 miles per hour at 1 second. 20 miles per hour at 2. 30 miles per hour at 3. And 40 miles per hour at t equals 4 seconds. And so we're looking at this and trying to figure out what the acceleration is. So it looks like my velocity, my delta V, is 10 miles per hour per second. That kind of looks funny, right? So my delta V per delta time. But this guy right here, that is my acceleration, 10 miles per hour per second. It looks funny. It doesn't follow this 10 meters per second squared like we're kind of used to seeing at this point. But yeah, that is acceleration. That I have a velocity changing per time. Now this next example, it's a little more straightforward here with what we're used to seeing. If I notice, I have something at rest to here. So that means my initial velocity is 0 meters per second. And my final velocity would be 16 meters per second. I have a time unit of 4 seconds that I'm working with here. So I'm going to plug this into my equation that I have up here. Remember, acceleration is Vf minus V naught over t. Plugging everything in. 16 meters per second minus 0 meters per second. All divided by my time, which is 4. And I get 4 meters per second squared for my acceleration for that particular problem here. Kind of makes sense. I have another one. This one is slowing down, so we didn't make a big deal out of that a second ago, but what's happening here is this thing is speeding up. So notice that my initial velocity is 0, and my final velocity was 16, so it got faster. So it kind of makes sense that my acceleration should be positive, right? It's kind of speeding up that way. Well, if I take a look at this next one, I have an initial velocity of 32 meters per second and a final velocity of 8 meters per second, both in this positive direction, a time interval of 4 seconds. Plugging into my acceleration equation, Vf minus V naught over t. I have Vf, which is 8, V naught, which is 32, over the time interval of 4 seconds. So take a look at this chunk right here. That's obviously going to give me a negative number here. So this gives me a negative 24 over 4. So it gives me an acceleration value of negative 6 meters per second squared. This negative value indicates the car was slowing down. So that's going to be a way you can check how you're doing your math and making sure all that works together. All right, so on this section right here, we're going to try to figure out which direction the acceleration is going. So we have a general rule of thumb up here. So to kind of read that, make sure we go through that. But general rule of thumb is if the velocity is positive and the acceleration is positive, that means I speed up in the positive direction. If velocity is negative and acceleration is positive, that means I'm slowing down in the negative direction. That's kind of a weird way to say that. Negative velocity, negative acceleration, I'm speeding up in the negative direction. And then I can have a positive velocity and a negative acceleration, and this would be slowing down in the positive direction. And so what I'm going to do I'm just going to go and mark these, the directions as positive or negatives, and want you guys to come in if you have a question, but these are just some general rules that we'd be looking at here. So if you take a look at these real quick, I have a positive, negative, up, away from goalie, up, leftward, and up for the bungee jumper, making sure we understand which direction those are. So kind of take a look at those, make sure you understand how those work. So on this little Hot Wheels question here, basically we're going to have directions using arrows, okay? And what's going on here is it looks like from A to B, the thing is accelerating downward, right? So the direction of the velocity vector, I'm going to say, is pointing to the southwest, right? If we're using our compass rose here. I'm sorry, southeast, right? So that'll be pointing to the southeast. And the reason, basically, it's simply the direction it's going, right? The acceleration is also going to be going this way. And the reason is it's speeding up. And so we want those two vector quantities pointing at the same direction. At position Y, notice it says the car continuously slows down from point B to C. So if I'm looking at point Y, the velocity is, I'm going to say it's to the east direction or to the right. And the reason is, once again, that is the direction of motion. That's the direction it's going. The acceleration vector on this one, I'm going to say it's pointing to the west or to the left of the object. And the reason is because it's slowing down, right? That part of the question told me that part is slowing down. At point Z, once again, the object is still slowing down, but it's telling me that the velocity vector is pointing to the left. So here I'm going to say west or left here. And once again, that's the direction of motion. That's the way it's pointing at me. And the acceleration vector, well, it's still slowing down. So from Z's point of view, it looks like the vector is pointing to the east or to the right. And once again, the object is still slowing down. The little race car is still slowing down here. So understanding which way vectors are pointing and all that is going to be super critical in how we attack most of our questions here. All right, for a bit of practice using our acceleration equations. So we have acceleration equals Vf minus V naught over t. And that's pretty much what we're going to be using the whole time. So when we do our questions here, I really want us to start filling in the givens here. So on this first one, what we're looking for is the time interval, right? So first thing I'm going to do is I'm going to fill in what I know. I know that acceleration is negative 4.1 meters per second squared. I know my initial velocity is 9 meters per second. And my final velocity is 0 meters per second. And I'm looking for the t. So the first thing I'm going to do is I'm going to solve this symbolically, or solve it for t, and it looks like this, Vf minus V naught over A. So plugging stuff in, Vf looks like it's 0. My V naught is 9. And my acceleration rate is negative 4.1. So when I plug that in, I should get about 2.2 seconds that the bus accelerated for. All right. Next one, kind of the same thing. I have an initial velocity of 7 meters per second. I have an acceleration of 2.5 meters per second squared. I want to get to a final velocity of 12. Once again, looking for the time. So I've already solved that. T equals Vf minus V naught over A. Plug stuff in. Vf is 12. V naught is 7. Acceleration is 2.5. So when I crunch my numbers, I get 2 seconds for this guy right here. All right, next one. So I kind of wrote out the givens here so we know what we're looking at. Once again, looking for the time. So we've already set it up. We'll go ahead and use that. So we have t is equal to vf, which is 0, minus my v naught, which is 6.5. Looks my acceleration is negative 1.2, negative because it's slowing down. So when I crunch my numbers, I get a value of about 5.42 seconds. All right. Okay, so in this one, it says it's kind of interesting, but when you run on a treadmill, remember, it's actually kind of running backwards, right? So I have an initial velocity of negative 1.2 meters per second. I have a time unit of 25 minutes. I have a velocity of negative 6.5 meters per second. So it looks like I should probably convert my minutes to seconds, probably be the easiest thing to do. So this is 1,500 seconds. It wants to know the average acceleration of the treadmill, so I'm using my acceleration formula, Vf minus V naught over t. So plug in what I know, Vf, negative 6.5, minus my V naught. So once again, I'm subtracting that negative. So negative of a negative is a positive, divided by my 1,500 seconds. So crunching some numbers, negative 6.5 plus 1.2 divided by this big 1,500 number. So I get a really small acceleration, but it kind of makes sense for the context of the problem. Negative 0.0035 meters per second squared that I would get for the treadmill.